Okay, let's talk about spread footings for columns. You should be watching this because you have already finished your soil testing and you're going to use that data to do some math for this activity. Okay, so spread column footing is pretty self-explanatory. The widened part of a foundation that spreads a column load over a broader area of soil. We're just distributing the weight. It's the same idea as snowshoes. So here's our load coming down from the rest of our building, and this is our spread footing that we're talking about, made out of concrete and reinforced rebar. This just shows all the different loads. Remember when we talked about roof loads, we talked about all the mechanical. Everything that's in our building finally makes its way to these columns that end up going down to a footing, and obviously they cannot sink. They have to support the weight from above. So we're going to talk about sizing a spread footing. It's based on a couple things: the total load applied to the soil, which we'll talk about, and then the allowable soil bearing capacity. If you look on your 343 soil testing, those guided notes that you have, or you can look on Canvas, on the first page on the right hand side you're going to see a table, and there's a similar one in this PowerPoint, I believe. Yep, this one. So after your soil testing, you came to the conclusion on the very last page where it says presentation of results. It's the second to last page and the last page. Through that, you figured out what type of soil that you have. Yeah, the very last page. If you look on the far right hand side, it says some acronyms like ML, CL, MH, and then if you look on the first page, you can tell what type of soil that is, either a bedrock or gravel or sand, and then that tells you this number. That's really important. So you'll need to have this number to do this activity. Okay, so if we go back, go ahead and write down this equation. This one's important. Q equals P over A, where Q equals the soil bearing pressure. P is the load capacity, or excuse me, the load applied, and A is the area of the footing. So if we know our soil bearing capacity, or the allowable soil bearing capacity, must be greater than or equal to the load applied. So this is just simply showing we're going to rearrange this equation because we want to solve for area. Our area must be greater than or equal to the load we apply divided by the allowable capacity of our soil. So this will be a big number that I'll show you in a minute. The entire load of the building, and this will be a number that we get from this chart. So really, this is the one we need to know. We're going to do this equation in another slide. Right now, you just need to know, I'm going to give you the thickness of a footing, and then we just need to, I'll mention this 150 pounds per cubic foot. That's how much the concrete weighs, and I'll reference that in a minute. Let's see, so we already wrote alright, here we go. Let's start on this picture. Just keep in mind, this beam and this beam and this girder and this girder, they're all transferring their weight to each of these columns. This one happens to be column B3. All that weight is being transferred there, and then of course being transferred to the ground. We're going to make some assumptions that have already been calculated. We're just going to use this for the sake of simplicity for this example. Let's pretend we already know our reactions of our girders and beams for the roof and the second floor. Here's kind of a cutaway view. Let me pull up all this. So we're assuming that we've done all these calculations. This is exactly like you did with MD Solids. We're not going to go through all that again, but they're just showing a roof and a second floor. You do need to realize this is times 2 because what they're talking about is, back at this picture, 2 beams, 2 girders. That's where they get that from. So that's why an interior beam times 2 and interior girder times 2. That's how we get these 2 numbers, and that's just for the roof. Then they do the same thing for the second floor. It has some different end reactions. And then they also incorporate the weight of the column. What you need to write down is this total column load. We're just going to assume we have this total column load of 112,500 pounds. Here's that calculation I said we were going to do. We're going to go ahead and write this one just as it is. So the load of our footing equals 1.75 feet. That's how thick the footing is, and it weighs 150 pounds per cubic foot, and that's how we get 262.5 pounds per square foot. So that's one piece of information we need to know. Next thing I'd like you to write is this equation. Our Q net equals our Q allowable minus the load, or P, of our footing. But this number, this 3,000, I don't necessarily want you to write. This is going to be for your soil. So look at your soil data. Again, I'm looking at the same guided notes that you have. If you look on the very last page, my example, when I did my soil testing, I ended up with a, yours might not be red. If you're looking at it on Canvas, it might be red, or if I gave you a color copy, it's red. But regardless, you'll see it's highlighted on the last page. It says sandy soil. Based on our conclusions on the soil testing I did, we ended up with a sandy soil. And that was, if you look across, it says SW, well-graded sand, various sizes of sand in our sample. So that's what we had. So if I go back to that chart, on the first page of your guided notes, mine was sand, and then it goes across, that would be 2,000 pounds. So your number could be 3,000 pounds. If you look at that chart again on the first page, if you had gravel or gravel with fines, it's 3,000 pounds, and then so on down the line, depending on what kind of soil you have. Depending on where you get your soil, and for the most part, they're going to be either gravel through sand with fines. I don't, in Utah, all the years I've been doing civil, I rarely ever get any samples that are silt, clay, or organics. Okay, so one more time. Take your number right here, subtract 262.5. Everybody's going to subtract 262.5. You're just subtracting the pressure of the pressure of the footing, and then you'll get our Q net. In this case, 2,737.5 PSF. Once you finish that, this is the kind of the punchline, the whole point. So I want everybody to write this equation. Then I would like everybody's going to use the 112,500. Everybody's going to use 112,500 pounds. This denominator, this could be different. If your soil capacity happened to be 3,000, well, then you're going to have this exact number. If it wasn't, you'll have a slightly different number. Then finally, the whole punchline is the area of our footing needs to be greater than or equal to 41.1 square feet. I'd like to see this in your notebook. This is a good reference. So depending on the site considerations, depending on some other variables, you could build a square, a rectangle, or a circular footing. Might not have the space for a rectangular one, that's why you might put a square one. It doesn't matter as long as the area is the same. So I'd like to see this in your notebook. And I'd like you to calculate the size of your footing. So you just found area. Take that and plug it into either a square, rectangular, or a circle. And I'd like to see the math for a footing. Again, I don't care which one. This one uses a square footing. They show you how they got all those numbers. That's an example for a round. And that's it. Make sure you have all those calculations in your notebook, and show me next time in class, or make sure you come with any questions you have if you're confuzzled on something.